Hey there, physical science students. This is Miss Ruark. We are in sound, and we're going to finish up this unit with this vodcast here, and then we're done. So, sound, wave. We've already talked about waves, and we know that waves can move in three different ways. They can move as straight lines, circles, or spheres. So, straight lines, an example of that would be the ocean waves. They all come in together in straight lines. You also have circles, which would be like ripples on a pond. And then you have spheres, which would be like sound waves moving through air, where these waves here are moving out. Let me get a different color. These waves here are moving out in a sphere from the dog's mouth, so it's got a 3-dimension to it. Okay. All right, so reflection, diffraction, and refraction. The difference between the three. So reflection is when something comes in, a wave strikes the surface and bounces off. So the wave strikes the surface and bounces off. All right, for diffraction is when the waves bend around an edge. So bending waves go around an edge, so they're bending around. The amount of bending is actually going to depend on a couple things. It's going to depend on the wavelength, and it's going to just depend on the size of the opening or the barrier that it's trying to go around. Okay. And then refraction, refraction is when the substance or the wave is bent through different mediums. Okay, such as if you were to put a straw into a glass of water and the straw looks like it's been moved in half. Okay. All right, interference is what happens when waves hit each other. And here we have, let's see. Okay, interference of sound waves. So when you have interference of sound waves, you can have compressions. Let's go to this one. Here we'd have the compressions are here and the rarefactions are here. And it's compressions of two different waves reach your ear. And when the compressions both reach your ear, the amplitude is going to increase and the loudness is going to increase because these are all hitting your ear together. The amplitude increases, it goes up. Okay, and then the loudness will go up as well. Well, if the compression of one, so if the compression of one and the rarefaction of another were to hit your ear at the same time, then the amplitude will decrease and it will get quieter. Okay, or the loudness will decrease. And this is, so the first one where the two reach together, where the two compressions reach together, that would be constructive interference. And then where the compression and the rarefaction both meet, it would be known as destructive interference. Okay, and here's another example of it where you have the two, where both of the crests reach at the same time, the amplitude goes up, and then this one where they cancel out. So constructive here, destructive here. Okay, standing waves. Oh, I also didn't tell you about this one. Sorry. On the interference of sound waves, loud versus soft. Okay. You can hear these things called beats, and it'll be a loud part versus a soft part. And I was trying to put a video on here, but it didn't work. And that's how you would actually be able to tune an instrument. And I'll show you that in class. All right, so standing waves. Standing waves happen when there's an interference between a wave and its reflected wave. And standing waves have nodes and antinodes. Remember, nodes means there's no wave, so that would be here where they're all crossing. And antinodes would be any part here along the wave that it's not crossing another one. Okay. Okay, sound waves. Sound waves are longitudinal waves. They're made by vibrating objects causing the surrounding medium to move. And in air, these sound waves spread out like a sphere. Once they reach your ear, the eardrum is going to vibrate. And how fast they move depends on the medium. It also depends on the temperature. Okay, so solids and liquids, they move faster because there's less space between the molecules, except in rubber. Rubber acts as a damper and it actually slows down the sound waves. So that's what they could use. That's one thing they could use for insulation. In gases, the molecules or the speed of the wave is slower because there's more space between the molecules. All right, loudness is determined by amplitude and distance from source, and the threshold of hearing is the quietest sound a human can hear. So it's going to go threshold of hearing. Well, the sounds can go from 0 decibels and up. Okay, so the hearing or the loudness of a sound is measured in decibels. The symbol is dB, little d, big B. And if it's increasing by 10, it's 2 times louder than it was the previous time. So if you have a noise that starts out at 10 decibels, okay, you'll hear that. And then if you have a next one that increases by 10, so it's 20 decibels, it's actually 2 times louder. All right. Pitch is determined by frequency. If you increase the frequency, the pitch goes up. If you decrease the frequency, the pitch goes down. Okay, and then infrasound and ultrasound. Infrasound is what's the sound that's below human hearing. It's below 20 hertz. And ultrasound is above what a human can hear, which is above 20,000 hertz. All right, musical instruments. So musical instruments produce sounds, and these sounds are produced by vibrations on strings, air columns, or membranes. So here's some pictures of some strings, just so that you could see them. Okay. And these musical instruments rely on sounding waves to make this, or standing waves to make a sound. Okay, so a guitar, the string will have 2 nodes and an antinode. And how that works is here, well, I guess it doesn't really show, but here's one node, and then if you hold down the fret here, it breaks the wave or breaks the string down, and so you have your 2 nodes. If you were to hold it or not hold it, but it was to this fret, then the nodes would go from line to line. So it has 2 nodes and an antinode, and you can change the pitch by shortening the strings. So you shorten the strings by putting your finger down on those different frets, and that raises the pitch of the sound. Fundamental frequency is the frequency of standing waves on a string. Okay, so the primary standing wave means that the wavelength is 2 times the length of the actual string. So if the string is, let's say, 100 centimeters, then the wavelength is 2 times the length of the string, so the wavelength would be 200 centimeters. Okay. And then in a flute, standing waves will form in the headpiece. And the headpiece is this part up here. It'll come apart, and what you do is you blow into that, or you actually don't blow into it, you blow across it, and it produces the standing waves that resonate from the node here down the flute. And you can make the wavelengths longer, which makes a lower sound, by holding down the holes, or closing the holes by holding down the keys, or you can allow those to get higher by holding the keys open. All right, resonance. Instruments use resonance to amplify the sound, and resonance is something that occurs when 2 objects naturally vibrate at the same frequency. Okay, so natural frequency depends on the object's size, shape, mass, and material. So look at 2 different guitars. An acoustic guitar would be considered a complex material, or a complex instrument, and it's going to resonate with a lot of natural frequencies. So you'll be able to get a lot of natural frequencies off of this acoustic guitar. It's going to amplify itself. Electric guitars, they're not going to amplify as well, so they would need to be hooked up to an amplifier to make the sound loud because they're more simple. Okay, the human ear. How do we sense these things? Well, the human ear will sense vibrations in the air, and those vibrations, those waves, will come towards the ear, and they will actually get smaller. And when they get smaller, they come through and they hit the eardrum. When they hit the eardrum starts to vibrate. Okay, the eardrum vibrating will then vibrate the hammer, the anvil, and the stirrup, which are the 3 bones in the middle ear. Okay, so the eardrum vibrates the hammer, the anvil, and the stirrup, the has, in the middle ear, the has. Just in case you can't remember, the has is in the middle ear. All right, the stirrup is going to hit the inner ear, and the inner ear will then vibrate to the cochlea. The cochlea is like a seashell-shaped structure that's inside the inner ear, and the cochlea is going to send these frequencies, or not these frequencies, these vibrations to the basilar membrane, which is not on here, but that's okay, which will resonate at natural frequencies, and lost my train of thought. Let's try that again. Okay, and the waves, the sound waves, the vibrations are going to be sent down these nerves, which are sitting which are sent through these little hair fibers, and it'll connect it to the brain and allow the brain to receive the symbol that a sound is coming in. Okay, hope you got all that. Whew. Okay, two last things we need to know about sound: ultrasound and then sonar. So ultrasound, remember its frequency is higher than 20,000 hertz. Most ultrasound waves pass through most materials. Some are going to be reflected, and it all depends on the density of the material. The more dense it is, the more chance it has to be reflected. Less dense it is, it'll go through. And these reflected waves will give these pictures. Okay, so these ultrasound waves pass through material and they bounce off of the more dense materials and come back. And that's how you end up with a sonogram of a baby, like this one here. This is a 3D sonogram of a baby. And so these waves are going through, they bounce off the baby and come back. It shows depth, it shows distance to give that depth, and it shows the contour of the child. It's also used to see inside the human body in other areas, not just for babies, but for if you're looking at your internal organs, or if you're looking for cysts or blockages, they can use ultrasound because there's no damage to the cells. Yay, that's a good thing. All right, so that is actually safer to use than x-rays because there's no damage. Okay, sonar. Sonar is used, uses reflected sound, and it measures distance. It's used underwater. So here's an example of a boat using sonar to detect how deep the sea is. The closer the sea level is, or the sea floor is, it's red, and then it changes from through the colors of the rainbow, Roy G. Biv, right? And the closer it is, or the deeper it is, the closer it is to the violet. All right, well, submarines can also use them to find things. And how they use this is they send out these sonar waves, and they wait to see the time it takes for it to reflect off of a surface. Now, that's going to count for the time it takes to get to the surface of a new object and the time it takes to get back to the detector, which means that you have to take that time and divide it by 2 in order to figure out the distance that the object is away. Okay, this is a lot of information. Hopefully it wasn't too much. I thought because we've talked about so many sounds and whatnot that Sonic Moo would be hilarious. It's not looking so funny right now, but go on ahead and laugh. All right, I'll see you in class.